Hi, welcome to part 2 of nuclear chemistry. Today we're going to learn about radioactive decay series. We're going to understand the different ways to detect radiation, the rates of radioactive decay. So we're going to go back to kinetics and we're going to apply only first order kinetics, so we don't have to worry about finding reaction orders because all of radioactivity is going to follow first order kinetics in terms of the rate. And then we're going to, in our Zoom meeting, do some calculations with radioactive dating. So we'll just kind of introduce that here. So just to reiterate, remember we have 5 types of radioactive decay. We have alpha, we have beta, and these are our 2 most common. Gamma is an energy that usually is associated with an alpha or beta decay. We have positron emission and electron capture. And now we've had some practice writing these nuclear reactions where one of these events has happened. But oftentimes when you have radioactive decay, you don't just have a single event. You'll have a series of events. These are aptly called radioactive decay series. Series meaning you're going to have multiple events, and they don't have to be the same. So some radioactive nuclei cannot be stable with only one decay. For example, uranium, the 238 isotope of uranium, decays in various steps to become eventually a stable lead atom. And it goes through many steps. And it can be different. So the end result is that lead is going to be the final result of that, but it doesn't have to go through the same set of steps. So here is a decay series for uranium-238 going to lead-206. And what you see here is there's a couple of branches along here. So the first one is uranium is going to undergo an alpha decay here and become Th234. Then there's 2 beta decays to get to uranium-234. Then there's 1, 2, 3, 4 more alpha decays. Now I'm at 218. And I can go either through a beta decay here or an alpha decay here. If I go through an alpha, I go alpha beta. If I go through beta, I'll go beta alpha, and then I'm going to end up at 214 bismuth. And then I have another decision tree. I can do a beta alpha or alpha beta, and then I get to lead-210. Then I get to another beta decay here, and then I have another set of steps here that I can go through. I can either do beta alpha or alpha beta and then get to lead-206. When I get here, this is finally, along this whole series, this is the first time that I've produced a stable nuclei. So at this point, that whole decay series is going to end. So it's going to continue to undergo radioactive decay until I get to a daughter nuclide that's stable, and then that process is going to stop. And it doesn't always go the same path. So one uranium could undergo mostly alpha decays here initially. Another one could mostly undergo the beta route here, but they're both going to end up in the same place. So this is a radioactive decay series where you can undergo a series of steps. This is something where if you were going to answer a question on this, you would have to be told, okay, so uranium underwent a set of decay series in this order, and it'd be like alpha, beta, beta, alpha, 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 beta, alpha. And then you could just, then if you knew the order, then you could write your decay series. But if you didn't, the only thing you know for sure is that that is going to decay until it gets to lead-206, and then that's where it's most stable, it's going to stop. A little bit of terminology here. Sometimes you'll see a element written this way. This is technurium, and you'll see this little M here. And this M is important because it means that this particular isotope is metastable. That doesn't mean that it's stable, but if you see metastable, then that means there's going to be a gap in time between your particle emission and your energy emission. So by particle, I mean alpha or beta, and by energy, I mean gamma. And so an example of this would be this metastable isotope here. So it's going to undergo gamma emission and become 99 Tc43 plus 00 gamma. This is still unstable and will undergo further decay, but the energy, the gamma energy that would be associated with that nuclear process has already been released. So now my 99 could undergo, let's say it undergoes alpha decay. Now it's going to emit an alpha particle, which is helium. This is going to go down by 2. This is going to go down by 4. And now I have nubium. And so these two events are going to happen, but if it's metastable, they're just going to happen at different times. So there's going to be a time gap between the two. If I wanted to write it all as one, this would imply that it happens all at the same time. This is alpha decay, but since this was metastable, this had actually left long before this event happened. So when you see this M here, that just means that the energy and the particle emission are separated from each other. One is going to happen before the other, and often it's going to be the energy that happens first and then the particle emission. This time can be very long. So I can have a gamma emission and then I can have this slow decay that happens over a really long amount of time, whereas the energy, the gamma ray emission, happened really quickly. All right, there's 3 ways that we can detect radioactivity. And if you've watched any movie, you've probably seen one or all 3 of these. The most common is a thing called a thermoluminescent dosimeter. This is usually used for workers who have prolonged exposure to radioactivity, and they'll use it as like a pen that'll be clipped on their lab coat or something like that, and then that detector, which is really small, something that the worker would wear, is taken off periodically and scanned for radioactivity. So it's a salt crystal with impurities, meaning that there's impurities in that salt crystal. So it's not just completely cation, anion, there's some impurities in there. And those impurities are going to trap energy. So I'm going to take this dosimeter, I'm going to wear it. And it's really portable and really small because it's just a crystal of salt. Let's say I wear it for a week, and then in a week I turn it in and they measure my exposure to radioactivity. How they do that is they heat this crystal up, and when they heat it up, these impurities that have trapped that high energy release energy, and then I have a detection system where I'm going to detect the energy that's being emitted when I heat that crystal up. And that's going to tell me how much exposure to radioactivity I've had in that amount of time. So dosimeters are really kind of low tech, but very easy to use and very easy to wear because they're very portable. The second one is a Geiger counter, and they're actually called Geiger-Müller counter. And this is a chamber. So this is a little bit more complicated, and it's a heavier piece of equipment, right? You carry it around, it has a little meter on it and a speaker, and it goes di-di-di-di-di. And as you get closer to something that's emitting radioactivity, it beeps more frequent and louder. These are really insistent. Okay, there is radioactivity nearby. How do they work? They work with an argon gas. So they have a chamber that has an argon gas in it. And if there is radioactivity happening, those particles are going to ionize the argon. So remember we talked about the ionizing power of all the different decays. So alpha decay had the highest ionizing power, but the lowest penetrating power. And so that ionizing power, if I have a inert gas and it's subjected to radioactivity, that radioactivity is going to ionize that gas. And so if I have a argon-filled gas container and there is some radioactivity that it has detected, it's going to ionize that argon. Ions in any scenario are able to carry an electrical current. And so once this is ionized, it produces an electrical signal, which is then connected to a sound, that's that counter. And the more ionizing, the more electrical signal, the greater that sound is going to be. And we also see like a counter on it. So I could have a sound or a counter, and both of those are going to measure that electrical signal. So the more ionization, the more radioactivity that's around, the more I'm going to ionize that argon, the more I'm going to detect an electrical signal. So that's the second way. A little bit bulky, you can't wear a Geiger counter around. And the other one is a scintillation counter. And these are made up of salts. So these are made up of sodium iodide or cesium iodide. As the radioactive species passes through these, they're going to emit UV or visible light because you're basically exciting those ions. The salt is going to release UV or visible light energy, and then I'm going to measure that and turn that into an electrical signal. So I might have a meter or something like that. So that's going to be that scintillation counter. It could be a counter or it could be a sound. So both of these counters can make noise. It just depends on what they're hooking that electrical signal up to. In most cases, it's doing both. So radioactivity is almost everywhere. So if I walked around with a scintillation counter, it's probably going to go off quite a bit because all the elements that are above a atomic number of 83 have the potential to have radioactive isotopes. So they are all around us, and so we are on a daily basis exposed to a lot of radioactivity. We're exposed to radioactivity that's coming from the sun, but we're also exposed to radioactivity in the elements that are around us. So over our lifetime, we can be exposed to quite a bit of radioactivity. This is all called background radiation, the small amounts of radioactivity that we're exposed to on a daily basis. If you are near a radioactive event, then that would be your measure of radioactive exposure, would be anything that's kind of above your background radioactivity, which you want to avoid. Kinetics of radioactive decay. So like I said before, we're going to use first order kinetic rate laws to talk about how this decay is happening. But unlike a chemical reaction, the rate of radioactive decay is not temperature dependent. And it isn't because it's not a chemical reaction. So remember what temperature did is temperature increased the number of collisions. So in a chemical reaction, if I increase the temperature, I'm going to increase the number of collisions of my reactants because I'm increasing their kinetic energy. So that's going to affect the rate. It's going to make it faster. Because remember, I have to collide in order for a reaction to happen. So anything that I do that increases the number of collisions is going to affect the rate. I can also decrease my activation energy by increasing temperature. So that's that activation barrier that you have to overcome to get from reactants to products. So let's say I have an endothermic reaction. This is going to be my activation energy here. And anything that lowers this is also going to make this reaction go faster. This is what happens in a chemical reaction. None of this is happening in a nuclear reaction because in a nuclear reaction, there is no activation energy here. There is only a decay as something goes from something less stable to more stable. And so all of these traditional things that we think about, we don't have any collisions that are happening. We don't have an activation energy. So temperature has no effect on a nuclear reaction. But we're going to treat it as first order because first order allows us to calculate the half-lives of these radioactive decays. So just to review first order kinetics, which wasn't that long ago, but seems like a long time ago. So remember, this is going to be kinetics that's temperature independent. So I'm not really going to care. If I had a chemical reaction, my first order kinetics would look like this, where this would be a 1, an understood 1, and this would be first order for reactant A. This would be my rate constant, and this would be my rate. All right, so I'm going to apply that to a nuclear reaction. So if I look at this in terms of what's happening in a nuclear process, I'm going to have a rate. This is now going to be my rate of decay, not my rate of production. I'm going to have little k. This is my decay constant, not my rate constant. It's my decay constant now. And then I'm going to have big N. And N is the number of radioactive nuclide. This is my parent. So remember, I go from parent to daughter in that nuclear reaction. This is my parent. So just like in kinetics, if K is large, my rate constant is large, then I have a quick decay, meaning the rate's fast. That's going to happen really fast. If K is small, then I'm going to have a slow decay, meaning that could happen over a year, 100 years, 1,000 years, 10,000 years. If K is small, this radioactive decay could happen really, really slowly. Remember over here on this side, my integrated rate law looks like this. ln of A at time t equals ln of A at time 0, the concentration of A at time 0 minus kT. So this is my integrated rate law for first order. I can also apply it over here. Instead of having concentration of my reactant, I'm going to have the number of nuclei. So I'm going to have ln n at time t minus ln n at time 0. So this is before decay has happened. This is the number that remains after time t has elapsed. I could write it this way. So just pulling this out. So ln nt over no equals negative kt. So I could write it this way. And this is often important because this is the ratio here. So let's say at 5 minutes, I've had 50% decay. That means that if this was 1 starting out, this is 0.5, and this whole thing is a 0.5 divided by 1, so 0.5. This is going to be my ratio. So sometimes I'm just solving for the ratio, or sometimes I'm solving for these individual components. One thing I can also substitute in, I can substitute in the number of nucleides, but I can also substitute in the rate. The rate at time t, the rate at time 0 equal to negative kt. The other thing to remember is my half-life reaction. So this is important too. So t1 half equals 0.693 divided by k. And we're going to use this a lot in this chapter. So this is for first order. These two here for first order. And then we could also do this substitution. So these are our first order kinetics equations that we're going to be using to solve in this chapter. And we're going to work on those problems together in when we come together in our Zoom meetings. So I'm not going to do any of those problems with you right now. And the last thing I wanted to talk about in this section was radioactive dating. So we use, and this is not some weird dating platform, but this is how we age materials. So there's 2 different types of radioactive dating, meaning I'm going to determine the age of a substance. And it depends if it's living, then I'm going to use carbon dating. Was it living at one point? If it was not living at one point, then I'm going to use uranium dating. And this is what we would use on rocks and things like that, whereas this would be what we would use for anything that has been living, that has ingested food, gone through metabolism. So this carbon dating is going to allow us to determine how old that is. Carbon dating looks like this. It's the most common. It's the one we hear most about because it kind of deals with really cool stuff. Rocks are not nearly as cool as things that were living. This is not found in nature, but rather it's made in the atmosphere. It reacts with oxygen to form CO2, which then goes into plants through photosynthesis. The tissues of all living plants and animals contain carbon-14. When the organism dies, it's no longer integrating carbon-14 into it, and at that point we start to have this process because we're no longer replenishing carbon-14. Now carbon-14 can start decaying into nitrogen-14, and then that is what we're going to use to be able to date that substance. We're going to look at the carbon-14 to carbon-12 ratio to determine the age. Because I know the half-life of this process is 5,715 years. That means that half of the initial starting concentration of carbon-14 I have has been converted into nitrogen-14 over 5,715 years. So this is a really long half-life, because then I have half of that is going to decay to this over another 5,715 years, and then half of the half that was left is going to decay. And so it's going to be a really long time before you have no carbon-14. The other one is uranium lead dating. And this is this process here where uranium goes to lead, and we said that this is a decay series, so this happens in many, many steps. The half-life for this is 4.5 times 10 to the 9 years. So this is useful for prehistoric things. So a prehistoric object that was never alive, rocks, things like that, are going to have naturally occurring uranium in it. Then we can look at how much lead 206 is in that substance, and we can compare and backdate it that way. Volcanic events deposit uranium in rocks and silt. Once it's incorporated, that's when the clock starts ticking. So uranium dating gives us the time at which that rock or whatever it was formed. All right, so we're going to stop here and we will pick up with part 3.